Hello, welcome everybody at this event about AI and machine learning. This is organized by the Smart Health Tech Center and Erasmus MC SQuAIRe. My name is Roelle de Koning and I work for the Smart Health Tech Center. I see some familiar faces, but also a lot of new faces, so I will briefly introduce the Smart Health Tech Center. And afterwards, I give the mic to Ihor to introduce EMC SQuAIRe. And then the floor is all for Gennady for this session of today. So in short, the Smart Health Tech Center is a new department of Erasmus MC. We exist for 1 year now. And what we do is we help companies, startups, SMEs, and other knowledge institutions that want to test or validate products in the field of smart health tech. So think about AI, robotics, virtual reality, wearables. And when they contact us, we try to connect them with the right experts, so clinicians, researchers of Erasmus MC, and with the right facilities. But also the other way around. So if you, as an Erasmus MC colleague, want to do something with a smart health tech company, you can reach out to us and we will help you to find the right company, and we can help you with the contracts and also with the pricing. So feel always free to contact us. Yeah, today's session is all about AI and machine learning, and I think this is a really good chance to ask all your questions to Gennady. For the introduction, I give the mic to Ihor.
Thanks. Thank you. Yes, so me, Genna, and Devika, we are part of the EMC SQuAIRe, so it's a Society for Quantitative AI Research. And Gennady today will give a talk about this subject. Our society, I see many familiar faces, so most of you know about the EMC SQuAIRe. We already exist for a couple of months. We hosted a few presentations. And the idea of the society is to create a network within the Erasmus MC, within the people who are doing something with machine learning, AI, artificial intelligence, and data analysis, and to bring people together, to share the knowledge, to connect to clinic better, to make this kind of basically healthy society and exchange of knowledge and ideas with different people. Today I want to present Gennady Roshchupkin. He's an assistant professor at the departments of radiology and epidemiology. He's leading the group on computational population biology. It's a group, he did a lot of things with machine learning, statistics, AI related to genetics, but also medical image analysis. He did a PhD at the Virus group, in the biomedical imaging group Rotterdam, so in the bigger. And he's also, lots of publications, involved in many consortia, leading work groups in the international consortia on data analysis and on AI. And yeah, today he will give it
more than enough.
Yeah.
For introduction. No, so, it's fine. Yes, thank you. Thank you for the introduction. I have my mic. So yes, so really happy to present today. And I think that, Igor actually introduced me and said something about research group. So unfortunately, I will not talk today about my specific research, as we discussed also with EMC SQuAIRe and also Smart Health Tech Center. So to have this joint seminar to actually introduce some basic knowledge, because we also in our community, we saw a lot of requests just to people want to learn or want to know the path, how to start to learn something, and some basic things. And of course, because we are located at Erasmus MC as a hospital, we have a lot of clinicians and colleagues. They might heard a lot of AI and machine learning, but they just sometimes afraid to ask, or just afraid that it's too complex, etc. So while it's not so easy, but it's also not so complex. And I think that today we'll give some introduction. And I think that idea that we can make it more interactive. So if you have any questions, you can ask during the presentation. I think that we can have some discussion, else we don't have like, we have some limit for time, but we can discuss questions. I think it's more important to answer the questions than just to show slides and then you go home and don't know didn't ask what you wanted to know. But first thing first, I think that just to mention that we have drinks afterwards, and Igor mentioned Vio Nissen. So today he actually has his like goodbye party here at Erasmus. So and since he was involved in all this AI and machine learning at Erasmus, he's departing to the Groningen as a dean. So he said we can crash his party, and after this lecture, we can come to the healthy food restaurant and have drinks and discussion there. I think you know. I think everyone knows where it is. So it's here at Erasmus, or we just can go all together. So, yes, okay. That's for the introduction, and now to the discussion, to the presentation. So. The idea is that, of course, we all hear all this AI revolution everywhere. So, and in industry, in e-commerce and online shops, and now I think most of the people, even in clinics and far away from machine learning, deep learning, heard about this ChatGPT and that how it can influence our life and creating some, I don't know, like artificial text which is difficult to recognize and almost as a human generated. So in other models, so it's everywhere. That's why this is a lot of discussion and I would say like some hype around this. But just to make it clear, because again, so this idea for this talk is to make it more like casual so we can discuss things and ask questions, but also to highlight that actually artificial intelligence, of course, is a buzzy word and sells good, but that's not what we most of the time talking about. Most of the time we're talking about machine learning on neural networks and deep learning. So, and that's why I think that quite some part of this presentation I will spend on some concept from machine learning, because that's easily translatable to the deep learning and neural networks. So, but I want to start a little bit with some history. So, and for me, so Igor introduced me, so I actually work at Department of Radiology and Department of Epidemiology. So I have more computer science background. That's why I look at this from the computer science perspective. I also have epidemiological education, so I will put this cap later during this presentation, this hat later. So, and I look at all this development actually from the algorithmic point of view. And I think that all of us familiar with the algorithms, like in daily life, right? So if you want to go shopping, you know, like you to dress, go outside, take money, I don't know, like buy groceries and go home, or how to brush your teeth, or like how to dress yourself. So, and that's why you have normally input to your algorithm, some rules, then you have some rules, and then you have outcome, right? So, and that's, I think that one of the issues people have when they start to program, also like interact with computer, that from one hand, we intuitively know what is it, but from other hand, sometimes it can be quite complex. So, and I just want to show this short video where I think this professor of computer science, he asked his children to make an algorithm how to make a sandwich. So, and that's...
Get 2 pieces of bread out. Got 'em. Get a butter knife and get some PB. Take 1 piece of bread, spread it around with the butter knife.
No, Dad, with the peanut butter.
I'm just doing what it says. It says take 1 piece of bread, spread it around with the butter knife.
Hold on.
Get some jelly, rub it on the other half of the bread.
No, Dad, open the jelly.
Well, it doesn't say to do that. Put the breads together on top of each other. Take a big bite. This doesn't taste like a peanut butter jelly sandwich.
Sorry, I had to make it extremely specific.
Oh, good. I'm starving. Take 2 pieces of white bread out of the bag. Take the lid off the jar of peanut butter. Get a butter knife and stick it inside of the peanut butter jar. With the knife, scoop a bit of peanut butter out of the...
That means like a lot.
A bit means a lot?
In my world.
There we go.
You're doing better than before, though.
Open the jelly jar. Squeeze it onto the other piece of bread.
No.
Done. Closer. Bread. Get some peanut butter. Take the peanut butter knife. Open the peanut butter. Put the knife in the PB. Get some jelly. Open the jelly.
No.
Squirt the jelly onto the bread.
You're supposed to...
Take the butter knife with the peanut butter on it. Wipe it all over the piece of bread that's blank. Take the butter knife, rub the jelly all over a piece of bread.
Oh, he's doing better. Oh.
That's all over. Put the two pieces on top of each other.
This is how I meant.
Take two pieces of white bread out of the bag. Take the lid off the jar of peanut butter. Get a butter knife and stick it inside of the peanut butter jar.
Yeah, I think that's a really good example in like how it works theoretically and practically, right? So, and I think that when you debug someone's code or like you debug your own code, sometimes it reminds you this conversation. So it just makes it just example. Actually, when we start with algorithms and translate it to real practice, it can be quite difficult. While intuitively it's really clear. So, and that's how it's all started. I mean, like before the machine learning and AI and deep learning, that's actually we had in place this expert system. So basically it was really complex set of rules programmed by the thousands or hundreds of engineers, and it just was really difficult, well, tasks. And there's this example with the video, so it could take like really years to define something. But that was not the main issue. One of the main issue, if you just imagine a simple example, is to answer this question, right? So let's say that if you have a computer, you have some rules, so, and you show that these three images and say, okay, what is there on these images? Like, how the computer, what kind of rules you can define, and to say that there's a cat or car or like an ocean, right? So that makes it quite difficult. So with all these rules, or you can think about some rules, I don't know, like if I ask you, like, how would you define for the computer to say, is there a cat or a car? What would you say? So how would you, like, based on the sandwich example, how would you define this in the rules? But what if it is a dog? Sorry? Okay. But if I show the dog, then it wouldn't. So that's why I mean that will get again so more complex and more complex, and we are not even talking about the thing like how would you actually recognize ears, right? So it's like for you, because what you describe actually it reminds me of this joke from the school test, right? Find X, here it is. So that's why it's quite complex. This task actually, which looks quite simple for human, like with. Like, yeah, there's a cat, there's a dog, well, that's simple. So that for the computer, when it translates to a set of rules, it becomes more and more complex and sometimes impossible. But that's not only one thing, like with this expert system, what is the issue. Another part is actually all this historical development. If I can name the major revolution in this history of this development, I would name the John von Neumann with his idea that what we now all use in our computers with like RAM and how we write the code in R, Python, MATLAB, you name it. So when we can really change actually the set of rules and execute them. So like write the code, change it, it's immediately executed. Before his ideas, actually it was more like a calculator. Everything is hard built in plates. So if not him, let's say, we might end now not with one computer, a laptop, which can make everything like PowerPoint, Skype, and run some browser. We could end up with like hundreds of different machines, one for Teams, one for presentation slides, one for this, one for that. So that would be really specialized. So and then what he did, he actually introduced the concept that you can execute all your code and algorithms in memory of the computer, and you can change it and adapt. So that's kind of lead the world to current development of this machine learning and deep learning algorithms and AI, what we're talking about. So just wanted to like some historical introduction to this. But what is machine learning? So right, so we start with this. So say that when we talk about machine learning, what do we assume by this? So because it sounds like, well, definitely not like this, right? We don't have like a robot sitting and reading books and learning something. So why we call this learning? And if I start with simple example when we have just a linear regression, right, task. So let's say that That's everyone uses it in statistical settings, right? I think most of the people familiar what is linear regression and how it works. But when we even simplify it more, so basically what we're doing with linear regression, if we have just, let's say, 2 points, 2 dots, right, 2 data points, and we have the equation. So basically what we want to do in linear regression, we want to estimate these parameters, M and B. And in classical statistics, there are ways to do this. So basically, if we just guess random these parameters, we can estimate and draw the line. We can estimate how far this line from these points. So, and in the classical statistics, there's ways. Well, we're not going to details in this, but there's like equations how you can exactly derive these parameters, and then you can exactly draw the line. So, but then it becomes more complex when we need something different. So, let's say in this simple example, with the 2 dots, let's say that we don't need machine learning, we don't need anything, we can use just classical statistics to estimate this. But then it becomes more complex in our research when we are talking about, let's say, collinearity problem, when we have more covariates than observations, or when we want to use more complex model and we want to model nonlinearity, relation, interaction between parameters, et cetera, and it becomes more and more complex, and there's no like defined statistical solution how we can do this. So then the question is, what is learning, right, in this setting? So what we want to learn. So if we want to ask computer, okay, we don't have exact solution, what we want computer to learn. And again, so a lot of things board, like say with later we'll talk about neural networks from neuroscience and the human being, and the same, let's say, example, how children learn, right? So they exposed to a lot of data, we give them correct answer, and they will pick up the pattern on their own how to actually learn something. So basically the same we want from the computer, so from these algorithms or settings. So let's say, come back to the same example. So let's assume that we don't have exact solution for this problem, right? So what we want to do, we want our algorithm to learn these 2 parameters some way. And the only way, as I described with this learning for children, to expose it to a lot of data, some examples, and then to optimize this. So basically, we can start with some guess, like on this example, draw the line to compute the error mistake, right, of this random initiation, and then to find a way to tune this, let's say, line to make it as close as possible to these dots. So basically, this learning process, when we talk about machine learning, it's not like learning with books and reading. It's more about to learn the parameters. So in this simple example, that's just to learn these 2 parameters. But when we have more complex model, it's like it can be millions of the parameters. And the principle, most of the time the same for machine learning or like neural network and the deep learning, is basically can follow up this simple diagram. When you start, you initiate some values, you compute these error values, right? You just find the way, which I don't cover here, how you can maximize this, how you can find the direction where you move your parameters, because it's a different topic and there are a lot of algorithms how to optimize this or maximize this. Then you check, is it close to the solution or not? And then if it's not, you go back. And in this case, you define yourself. So say how close you want your model to be true to these dots, right? So say if we're going back, so let's say if you keep iterating, so say how close this green line you want to be to these 2 dots. So let's say, because you don't want to make maybe it's too close and then too far. So there should be some balance in how long you want to optimize this. Because again, so when you translate everything to the, let's say, computer language, so it takes some time and some iteration to compute and get these parameters. Some questions so far? Because normally people asking questions about learning, and I was trying to make it as simple as possible. So, yeah, but no questions. Okay. So now when we talk about, well, major components of machine learning, So we can split it basically in 4 things. So it's like about data, as I mentioned, about model selection, which I will cover later, about features, which is also, if you're familiar with epidemiology, it's more about variables selection and training process. And if we go in the types of the machine learning, so that's, again, so say if you will hear some buzzwords later and you want to learn more about this, so you should consider that, well, there are major, let's say, 4 directions for machine learning algorithm. It's either supervised, when you have basically some labels or you want to predict some values. So basically you have the correct outcome and you want to build a model which will predict following values or let's say similar classes. You can have unsupervised when you actually don't have true values and you want to basically define some data-driven algorithm which will do this for you, let's say, to find the clusters in your data. So if you work with some population-based data or, I don't know, like omics data, so you want to find all disease patients, so you want to find other different subtypes of disease. So this can be application of the unsupervised learning. Like semi-supervised, there are different techniques when you can combine, let's say, this supervised and unsupervised when you might not have all data or all annotation data, and you can use some tricks and some algorithm to do this. And last one is reinforcement learning, which basically learn from mistakes. So basically reinforcement learning normally used for some robotics or like self-driving cars and all this technology. So it's not so, let's say, widely used in clinical studies when you do some research. But this is just more broad, let's say, classification. But also if I said, so let's say that, okay, this is about the type of the machine learning. But then if you go to the task, what machine learning can do, so then normally you have first a problem, right? And then when you want to find a solution, because I think that I always, when discussion about this fancy algorithms, it's more about that you have to answer the question what you have instead of just using some fancy model because everyone uses it or because it's popular or because of some other reason. So that especially in healthcare settings, first you need to ask the question, let's say what you want to do. Is it like classification problem? So you have some diseases or some image with some, let's say, tumor, not tumor, etc. Is it like a regression problem? So you want to predict certain value or like fit a model for the prediction of this continuous variable. So is it like clustering, as I said, so let's say that unsupervised, so you want to define some clusters in your data. Or let's say you have too much data and you think that too much parameters or variables, and you want to reduce the dimensionality, so you want to get less and more informative for your task. So let's say to increase statistical power, etc., etc. And this is a really nice diagram for scikit-learn. This is a Python library. I will mention it later. So I think that's the most popular use in Python for machine learning, classical machine learning. So it's open source library. There's really a lot of documentation and examples. So if you want to dive deeper in all these examples, I think that's the way to start. And I like this diagram because it's also honest. Let's say it starts immediately. Let's say if you have less than 50 samples, so you need more data. So sometimes you can't do anything if you, of course, certain situations at 50 maybe it's like arbitrarily defined, but let's say it's also important to realize if you don't have enough data and you haven't collected enough data, so maybe it's better to collect more data than just trying to find a fancy way or like overfit your data, etc., etc. But another part, what is also important, and that's what people when saying all this, let's say this machine learning, so let's say it's about the training, right? So let's say we show the model the examples, and the model takes some guesses. We know, let's say, to tell the algorithm is it right or not, and the model learns how to write weight parameter to estimate the parameters, and let's say to make it like a regression, classification, and all these tasks what I showed before. But then the question is, yeah, why we can't just take the most complex model, dump all our data, and we're done, right? So like that sounds really good way to do this. And the thing is, so that's not so simple, right? So that's again, so say that, as I said, it's important to realize what kind of problem you have, and also what kind of model. When I mention model selection, it's also, oh yes, is it animation, right? Yes. So say in this example again, so we have just linear regression of some trend line, and on the left side, you have really much complex model, right, which fits all the data perfectly, and your error basically 0. And another one, just a line, it's not so perfect. Which one would you use in your research? Sorry? That's a question not for you. Yeah, so just to, any guesses? Why?
Because the left one is overfit, it won't predict anything. If you assume, if you look at it and you think it's a line, there will be points which are on the right, it would fit roughly to the right line on the right. But if you put it on the left, it will just completely not fit. A perfect fit in this case doesn't predict really anything. It's just too good.
Okay. Does everyone agree? Or is it you agree or you don't? Is it like clear, super clear, or not? Yeah. So okay. Okay. So yes. So that's the correct thing. So basically, if we actually, so that's okay. We have some set of data, right? So we feed the model. It's really perfect, like on the left side. On the right side, less perfect. But when we, let's say, collect new data from patients and input to the model, and we recompute the error, you see that actually the left one was too perfect, and what was mentioned, overfitting, and that's why new points is just all over the places, and then you get a really high error. So while on the right side, so the model was not so perfect originally, but it keeps this not perfect error, let's say, value in the same, let's say, an interval. So and that's why I think that it's important, this concept of overfitting when you have a machine learning models or like neural networks, etc. So then it's not so easy. So you can choose the model which will be too simple, and then actually you don't do as good as you could. But you can make it too complex, and then actually you just overfit it on your data. And that's, while it looks on these examples quite simple, I will show you later some example even in the industry and in production where people like hundreds of engineers don't know these basic sometimes things. So and that's why when we talk about the accuracy of the model, we basically have to consider two things. It's about the variance and about the bias. So, and this is like really famous plots, I mean, the way to show this. So you have these bullet shots, right? So if you like the top left is the perfect example. You don't have variance, you don't have bias. And sometimes you can have really low variance, but really high bias. So it's at the bottom left. So sometimes you can have like spread around the center, so say high variance and low bias. And all this time you have this situation. So say when you train your model, you evaluate the prediction and see how it works. And if we come back to the complexity, so there's always a trade-off between how complex you want to make your model and how much variance and bias you get. So basically, you need to find the optimal complexity to like kind of, there's no golden standard, but to find when you don't have too much bias and too much variance. But that's talking about the classical, let's say, machine learning, what people talk about variance and bias. So now, as I said, so say what in clinical settings and healthcare, and also actually outside healthcare, people don't consider that there is a different kind of definition of the variance and bias. And here, actually, I can put my head of the epidemiologist and talk about, well, epidemiological study when you have informativeness of the study. So the first thing what is important, of course, is prior knowledge, how you design study, etc. But other things, what we're talking about, actually, which looks similar but a little bit different, is about validity. So it's like systematic error or bias again, or precision, it's a random error. So we can use the same things, the same like bullet points here to say that validity is the same bias, so, and precision about the random error. So this is from epidemiology known for like 150 years, so basically, and in machine learning community and AI people sometimes not aware of this in the study designs, etc. Another thing from epidemiology, which is also important, it's about external validity. So basically what people used is, okay, I did some model internally, so I train it, it looks like I don't have high bias, high variance, so, and then in epidemiology, it's normal thing is you have external validity, so replication study. So basically the same things what people use in classical machine learning and deep learning, it's about training validation sets. So even so, to avoid this overfitting and overcomplexity of your model, so basically you need to have to split your data set on different chunks, let's say. On one, you train your data. On additional, you validate. Well, in perfect case scenario, you have also test set. And there are other techniques like cross-validation, etc. I'm not going to talk about this in details, it will take too long. But let's say the way how in classical epidemiology people have this external validation or replication to avoid this overfitting, or just on your data set, like you collect it in one hospital, and it's not translatable to another hospital at all, let's say with images or even population-based study. So it's like from Netherlands to US or like Asia or some other countries. So, but what is actually people sometimes don't realize in a classical, let's say, machine learning, etc. So that if we come back about precision, so people say like, I need just more data. Give me more data and everything will work better. So if I talk with the students from sometimes some lecture or discussion in Delft, they just say, I don't want to know about healthcare, now all these details about biology, genetics, you name it. Just I know how to write a code, give me more data, and I know how to like optimize, and everything gets fine. So, but the point is, there's such saying that garbage in, garbage out, right? So basically, what you can do with more data, you can improve precision or variance. But what you can't do, avoid bias. So if you collected data in the wrong way, you will still have a bias. So it doesn't matter if you have 1 million patients, 2 million, 10 million patients, you will still have this bias. So and there are a lot of examples how people don't do this in the right way, or like don't consider these classical epidemiological things in production. So in one of the famous example from industry is actually about historical bias. So when, well, Amazon, they have a lot of employees, so, and in some moment they wanted, yeah, we have too much work for HR, let's just optimize how to select candidates based on CV, because we already have like years of experience, all the data collected, let's just translate what we did in 19th and 2005 to 2020. So and what happened is, they trained the algorithm to select the candidate, and it happened that algorithm started to select only males. So and why that? Because in 90s, historically, there was more engineers, males. So basically, they trained the algorithm based on the some things the algorithm can extract from the CVs, that is like a male candidate, and then I have to prefer males over females. So, and that's just because they have thousands of the CVs, thousands of like examples, but historically, it was collected wrong. That's why you can't use this data without, let's say, cleaning them and like making a proper study design. But there are many examples, not only, let's say, in the companies, but also like in the publications or some method in healthcare, right? There are a lot of, for instance, tools now, they are trying to make diagnosis of based on the audio data, for like Alzheimer's disease or Parkinson. But let's assume that they haven't trained algorithm on different accents of the people or even different ethnicity, because let's say then it's basically will be completely wrong or over predicting that someone will develop or under predicting. So, and that's if you collect, I know example from companies when they say we just want to use audiobooks. It's a perfect example. You have text and audio. So let's train the algorithm. And then it happened that again, so most of the audiobooks, they are, I'll say, the voices there is like white Caucasian people. So they have, let's say, that American accent. So and then you have a huge bias, and you can't recognize different accents or different intensities. And most recent examples also with image analysis is you have examples where people, let's say, don't consider for skin cancer detection different actual skin colors, or let's say one of my favorite example with the COVID severity prediction, when people publish paper and say we can predict like 99% accurate that someone will die from COVID based on the X-rays, but it happened that they trained the algorithm on the set where everyone who would die was laying during the X-ray, and everyone who would survive was standing. So basically, the algorithm learned just to recognize the position of the body instead of severity of the COVID. And that's why I think these things is really important when you start even designing your model and study design to consider before you even go deeper in the analysis. Because let's say we come back to this diagram, there are a lot of different ways and algorithms you can do, but like you can go, of course, details and learn about this, but nowadays there are even like frameworks, and this is example from Erasmus MC public group, where actually you can just input your image and the algorithm, this framework will run all these hundreds different algorithms from machine learning to do the prediction, extract features, all the type of the features, texture, shape, intensity, pull all together, train, retrain, find the best algorithm which fits to your data. But if you input the wrong data as a researcher or a clinician, then of course it will find something, but will it be useful and informative and actually reproducible somewhere else? So that's why it's important to know about these algorithms, but also important to realize that like domain knowledge and prior knowledge is essential in this work. Are there any questions?
I had a question. You said, well, data is essential. Rubbish in, rubbish out.
Quality of data. Or
Quality of data. It's also that with machine learning you can automatically also improve the data before you start?
Oh, that's a tricky question. The question is, can you use some machine learning algorithm, or machine learning algorithms, let's say, to actually QC the data, right? Yeah, but then you end up at that you first should know what you want to QC. So it's more about that you can automate some labor-intensive work, like QC images, if you have like hundreds of thousands of some scans, and you want to really select the one which is good quality for your analysis, that's possible. But if you don't know what you want to find, that can be quite tricky. So
Sometimes you also have, of course, data sets of patients, and then there are things missing in the set.
yes. But then again, so that's the same, I think that that goes to the classical statistical imputation, right? I was always also like surprised and amazed on this imputation method. So if the variable is not so important, let's say it's not your major outcome, of course you can use some estimation, let's say mean value, like what is most popular in epidemiology. So the same, there are some imputation methods for like more complex data. But then the question is how well this will represent what you want to learn. So basically, I wouldn't suggest to generate some data and then to learn something new from this. So that's a tricky point. Of course, I mean that also like what I think that you also mean is sometimes synthetic data, right? So, but that's we had, yeah, that's we had discussion. So say that's.
There's a lot of discussion, of course. You have big projects, and sometimes you have on certain patients with just missing data. Of course, that's something that everybody is puzzled about. What to do with missing data in a data set?
Yes, yes. So, but again, so say this is if it's like essential missing parameter, like say your outcome, like you want to predict disease and you don't know the status of the, say for some patients, I know, like you don't know was it like did this patient develop certain disease or not, and then you want to impute this, that can be tricky because you might introduce more noise and bias in your data set. Then you would better to use small data set but with more accurate data than with this. So that can be difficult. Okay. Yes.
Yes, hello. So you say for the garbage in, garbage out, and this is like you present here, I don't know this, but some package where you throw in data
Yeah.
and results out, I guess. And that loses sort of the interactiveness with your data, and so if you throw in garbage, you also get garbage. But how would you suggest to figure out if your data is garbage, or what part of your data is garbage, before you do any machine learning?
Yeah, I mean, I think that there's maybe to differentiate like data garbage, like you have, I know, like you, instead of, in this case, like liver MRI, you have brain MRI, I don't know, so something like that. That's, of course, one question about the QC of your data, and that's, as a specialist, you should basically find a way to QC data, either manually or like, say, automatic or semi-automatic. But another thing, what I was talking is more about the biases, how you collected data. So that's the garbage. Let's say if you collected, in this example, liver, let's say, images only from, again, from male patient, and you know that there is a difference of the prevalence or the speed of tumor growing in between males and females, as the oncologist or like radiologist, then you know that you can't do this accurate for the for the whole patients. So you just either you say, okay, I can do this only for male patient now because I don't have enough data for females. Like the same, for instance, now in
So you need prior knowledge.
Yeah. So that's what I'm advocating for, is like the prior knowledge, sometimes more important than knowledge about these algorithms in a way, because
I'm a bit busy with mostly unsupervised learning, but then you do not really have prior knowledge. You're looking for clusters and trying to find out if they have some meaning.
Yeah, but then, for instance, with clusters, you eventually evaluate this. Like you found, let's say you have some cell type, like I don't know, like a single cell analysis or something, and then you found some clusters. You still will try to find, even for publication eventually, like something is what is known and something new, right? So if you found something completely random and nobody knew this before, let's say based on literature or some like more zoomed research, that sounds a bit suspicious, right? So you will still evaluate your results eventually based on the prior knowledge. So because otherwise you end up with, I found 10 clusters of patients, here you go. And yeah. Oh.
Even naar de andere kant van de zaal.
Thank you for at least for this part of the presentation. In classical statistics, you want to look at the model, all your betas, and then you understand what the model is about. Shouldn't we also be better understanding the models we are producing, and then also this bias can be maybe tackled?
Yes, well, that's a good question. A bit more. It's also like a complex question. It's about the interpretability and explainable AI, or like now it's explainable AI or explainable machine learning. Let's say with some machine learning algorithms, you can get this information. So you can get some betas, features, importance, and parameters. With, let's say, more neural networks and deep learning, it's more complex, but there are like ways to do this, and actually it's also a hot topic, like explainable AI. But another thing is to consider there is a difference between interpretable and explainable. So, you can explain something. Let's say I can tell that, I know, like this shape is important for the prediction of severity, right? But if for you, as a domain knowledge expert, the shape doesn't say anything, like how you would interpret this. So you know why, but you basically don't know what does it mean. So that's why it's a different layer of this interpretability and explainability. So I would say.
I can explain.
Yeah, but there are people like working on this. So that's one of the discussions, especially in the healthcare sector, I think. Yes. Okay. Shall we move? Because this actually was part about machine learning and some basic concepts what you should consider about the models, etc. Of course, I will give at the end some literature and some sources you can learn much more about this, because in the like 40, 50 minutes it's difficult to cover this. But some things to mention about another, let's say, type of the algorithms, or like what we're talking when I showed this diagram with AI, right? Machine learning and neural network and deep learning is a subset of this. So when we're talking about the neural networks, why it's so important, how come? So, and I think that one of the things why it became so, let's say, powerful, it's the existence of this universal approximation theorem. So which basically says that with one layer neural network, you can approximate any function. And by function, it means like any input and output, right? So, but the tricky moment of this theorem that theoretically is possible, but it doesn't say how many neurons and how to fit this model. So that's why we have now a lot of different architectures and a way to do this. But in a way, that theorem shows that basically if you have a right architecture and a right neural network, you can replace other machine learning algorithms. So, but the question is why now it becomes more and more popular, or the neural networks basically, they took over other classical. And actually the history of the development is quite long. So it started in 50s, 40s with, well, I'm not going to cover these terms in some, let's say, researchers, but it started a long time ago. Actually, was also really optimistic that we will develop like in the 50s already, like artificial intelligence, and will live in the future. But it didn't happen, so it took quite some time, and like this diagram deep learning in 2010. Now, let's say, I can say that maybe next step it will be these transformers, which now used everywhere for natural language processing, but also for imaging, etc. But there are like theoretical development and practical. And practically again, so there are several things why it's happening right now, happened in the last decade. It's about the data, because all these algorithms, they require a lot of data. And I think that, well, with storage-wise and the internet, etc., we just accumulated as humanity a lot of data, not only in healthcare, but outside the world. So that's why it's happening now. Another thing is about computing power, all these GPU cards in the last decade and accelerating, so that gave us option that we can use these supercomputers basically and the GPUs to run all these algorithms, because one thing is the theoretical knowledge and another thing is practical, how long it takes to optimize all these parameters, etc., etc. So, and the last part, of course, develop slightly new types of the algorithm based on this data and computation power. And one of the example, like with the deep learning and fully connected deep learning neural networks, which a bit flip the traditional way how we think about this. So if I was talking in the beginning about the algorithms where you have defined a set of rules, then we talked about machine learning where, well, you have to select the model, you have to find the complexity of the model, some features, input, output. So basically how the deep learning and neural network change it, they change it in a way that you don't need to care now about the feature extraction. So basically if the classical machine learning, you have some input data, let's say to classify, is it a car or not car? So you need to define some features. Again, so as we discussed, let's say, there's how many wheels, are there windows, I don't know, whatever color. So you do this prediction, and then deep learning, you basically input just image, and it can do this magic for you. So basically, if we come back to this example, so and we discussed before that let's define, I don't know, do you have ears, cars, like something else between dogs and cats? So with neural networks and deep learning, you don't care about this. You just input image, you have labels, and the algorithm can automatically define some features and parameters from image, which is actually coming back to the interpretability and explainability, might reflect this like ears or eyes, etc. But most of the time it's some random shapes, not random shapes, but like very difficult to interpret it for human being, let's say, that how this feature looks like and why they look like this. So of course there can be some, you know, like features about like, is it like circles and some edges on the image, But if it's more complex task, it's really difficult to interpret why this was selected. But again, so given the whole complexity of this topic and also time-wise, I don't want to can't cover everything, but I just want to show that the basic things of the neural networks and the deep learning is basically based on this diagram, or let's say classical deep learning architecture, where you have input data, you have input layer, you have some hidden layers which you can define as deep as you want, and they like all these bolts here, it's neurons. I will go this later. So and then you have output, and output again can be a task for classification, can be task for regression, and some other things. So, but again, so the basic concept that comes back actually to the neuroscience and idea of the neuron, that all these balls on these spheres, let's say, on this diagram architecture, is just what we call neurons, and they have some input parameters. So let's say they have some output. So, and if you look at this like this, so one neuron, if you have just neural network with one neuron, it actually represents just a linear regression. So you have some intercept as 0, then you have some betas, x1, x2. That's basically how it works. So basically one neuron is just a linear regression. So if you want to make it more complex, because, well, not linear regression, but also a logistic regression, like multi-class classification, then you can just apply some function to your neuron and say, well, just make one neuron look like a logistic regression. So basically, if you go back, well, if you make the analogy with neuroscience, and I hope they can correct me, does it look familiar? No? Okay. So, yeah, so it's not my picture. So I will blame someone else. No. So basically, that's the whole idea. So you have some input to your neuron. So you have some parameters. Let's say this W1, depending on how many input parameters you have some activation function. It can be just nothing linear. So it's like if it's for regression, and it can be sigmoid for logistic regression. And then you build, basically, if I go back, to hold these connections is this propagating of this function and signal. So from input through all neurons to the output. But again, so say just not to forget that we apply the same principles after we define the architecture, that first we need to train the model. So we define the architecture with input data and output. So we go through the same, well, there are some algorithms how to do this. And we need to take care again about the training, validation, and not overfit the model, because that's the same when sometimes I talk about neural networks, people forget that actually training and validating your set, and then you apply it, you actually apply it on the data you didn't train it on. So, but of course, that example was kind of one-dimensional example, but you are not restricted to 1 dimension or 2 dimensions, 3 dimension can be as many input as possible. And I like this animation. So basically, this is example about how the neural network, after it was trained, works for handwritten digits classification. So your input just, I think it's a 52 by 52 pixel image, and it's all connected, and there are like 3-4 layers, and you see that basically each pixel is just a number, right? So it's like one parameter. So and you see how the signal propagate, goes via these neurons. Some of them, let's say, highlight, then they activate it, so the signal goes further. And then at the end, you have just 10 classes or 10 outputs, and then the most probable one just highlighted. So that's just example of the, well, a bit more complex than 1 dimension, but 2-dimensional fully connected neural network. But of course, nowadays, there's a whole zoo of different architectures, and they use for different purposes. Again, well, as I started actually that neural network and deep learning kind of solve the problem of machine learning, now you can just use it. Well, it's not exactly true, because now you have a different problem, you have also different type of the architectures. So, and they also use for different tasks. So, and well, if I would name 3 main types of neural networks you should maybe think about. It's just classical feed-forward neural network, what I just showed you. That convolutional, it's on the right actually, convolutional neural network. That's one used a lot for image and video recognition, classification, and another one, recurrent neural networks, or now for neural language processing. So that's kind of direction now. Recurrent networks, they are replaced by the transformers. But idea again, so the same is for originally was developed for neural language processing. And if I can show one example, which is always amazed me, with application actually in healthcare. When I started PhD, it was in 2014 actually, and it's a long time ago. But it was people working on the whole thesis, like in radiology, was based on the task for white matter lesion segmentation. So what is my white matter lesion? It's like you have a brain MRI, and you want to automatically segment these white spots. Let's make it simple. And it could be like the whole thesis just based on the best machine learning algorithm, how you optimize some parameters, some machine learning algorithm, like it's like a support vector machine, random forest, whatever, you name it. And nowadays, with deep learning networks, normally I give it as a task for students for some practicals. Within 2 hours, they can make state-of-the-art segmentation. So, and that's just within like 10 years. So actually that could happen even like within, so from 2014, I think people finished in PhD, and then 2016 it was already done by deep learning much better. But again, there are a lot of things what we actually have to discuss, and that's I think all idea of these seminars in more depth and details, and there's some questions to ask, and just again to mention this explainability, ethical issues, biases, unexpected behavior, data privacy, adversarial attacks. I think that's also for healthcare can be relevant, especially if you start to work with other collaborators and don't want to share data and privacy. Because, and why I actually spent time on some concepts of the bias also and study design, etc. Because let's say practically, if you want to write nowadays just deep learning algorithm, so this is this state-of-the-art neural network for white matter segmentation. It takes just, I don't know, 30 lines of Python code. So it's not a big problem to write a code now and to make it run and do something, but it's much more problem what you run, how you run, and why. So that's why I think that's important to consider. So, and it takes 80% of the time before you start to run something. And some resources I want to mention just at the end. So of course there are a lot of courses online. There are a few books. I think we will share the presentation after so you can check these books, and some libraries. If you prefer video, I would really recommend actually Andrei Karpathy. He has a YouTube channel, Zero to Hero. He was ex-AI lead at Tesla. So he quit just recently. There's a full stack deep learning from Berkeley course and practical deep learning for coders from Jeremy Howard. He has really good online course also, fast.ai. So, but he has also YouTube channel for more like practical things. So I think it's interesting to check. Because again, so in 1 hour, it's impossible to cover this and to learn everything. And I think with this, I want to finish and thank you. If you have any more questions, I'm happy to answer.
I think there's still time for questions.
Yeah. Yes. I hope they didn't drink and ate everything, right?
Thank you for your presentation. I think we've all seen in the news or on the internet how robust and strong artificial intelligence is becoming. And most of the time it's used to find some correlation or fit function to show that things are correlated. Is it also possible to, with extensive enough research, and running enough models with different complexities to show that some correlation is not there, so that the information is not in the images you're using or something like that?
Oh, okay. So you mean that to say that something doesn't exist?
Yeah, not in the data that you're using, yes.
Oof, I think that's, it's a tricky question because, of course, well, it comes up with the same like when classical study with power, right? So if you have some, again, prior knowledge and expectation that with certain amount of data, you should find this pattern. If it's not there, then you just use the wrong data. But I wouldn't say that you need to run a lot of models, etc. But it's again about your prior knowledge, and is it possible to do not? So that's, but that's a tricky question. I mean, that because normally also, I think the same with interpretability. So it's much easier to say that there is something because all these algorithms are greedy. So let's say if you found something and you say this feature parameter is important for prediction or classification, it doesn't mean that something else is not important. So that's much more tricky to say, and you have to do some extra tests, let's say, and there are some ways to do this, to say that other feature is not important. Like if you take it out or like replace some, let's say, part of the image, etc. But in general, it's easy to say that what is important, what is not, than to say that something is not important. Or,
okay,
yeah.
Thank you.
Sorry?
Then you can say it's not there in the data. You can also do it the other way around. You can have data that shows that if you shuffle the data in a certain way, that effect goes away. So that's another way to show that this isn't real. These are very important tests you should do for your networks.
No more questions?
Okay.
Well, if there are no
Thank you.
questions, then we are going for a party crash at Wiros, I think.
Yes. Thank you. Thank you so much.
Okay, so please follow us for the drinks.